Hey everybody, this is Chris. Sean and I chose to study FEA, or finite element analysis, and how FEA uses the implementation of eigenvalues to determine different failure modes, critical values, and other things we'll go over in this presentation. So hope you guys enjoy. Leave some comments and what you did or did not enjoy, and let's get started. So what exactly is FEA? If you haven't used it before, which I'm sure everybody has because we're all mechanical engineers, I think maybe I'm wrong on that. I'm a mechanical engineer. I've used FEA. It's a very important software where we can it provides a lot of tools to simulate and predict failure modes and different load scenarios. So we can therefore take those outcomes and safety factors and different factors like that to optimize structural performance of systems under different types of conditions. FEA uses eigenvalue analysis, particularly when assessing structural stability and different behaviors in dynamic and static systems. This report we put together goes over a few of those applications and from different studies we found throughout this project. So we're going to explore some of those FEA examples and eigenvalue use on buckling analysis of pressure vessel systems, and also on porosity and buckling failures on functionally graded material panels. So FEA is mainly a simulation of changing natural frequencies, critical values, such as material or thicknesses or different strengths, and then also design characteristics in different 3D models and their effects on the designs and structures that they have. Modal analysis with eigenvalue mathematics is a key factor in what FEA does, and its relation to key loads and failure scenarios. So let's do a quick little introduction of some of the projects we found. In our paper here and in this presentation, we'll be going over some of the aspects of that. We go over 2 real-world examples, and then we also throw in a few extra applications at the end. The first of those examples was torus spherical enclosed pressure vessels and failure modes also in functionally graded material panels, different structures. So for the pressure vessels, we explore how critical eigenvalues can help determine critical buckling values and help our aid in understanding in the design, and also go into the eigenvector and eigenvalue analysis used in the FEA to determine these critical values. So for the FG panels, or functionally graded panels, we looked at a study done by a few different people, referenced at the end. You can see the authors in the study itself, and it really focuses on the effect of porosity, material grades, internal cracks and defects, and how that affects natural frequencies and critical buckling loads of these panels. So those natural frequencies we can determine from natural critical eigenvalues, and this goes hand in hand with other different examples of complex real-world scenarios, because these FG panels are seen in a lot of different places. We looked at this model a little bit, and eigenvalue analysis can be applied to determine different vibration characteristics of these systems. The other example we looked at was torus spherical enclosed pressure vessels. So we looked at the different critical buckling pressures, which we determined through a series of equations. We chose to go further in depth with this problem, so we'll go into that with our mathematical approach, and we overall will see that these eigenvalues help us design appropriately to withstand whatever loads that we may be designing that part for. So part of that project, these pressure vessels are seen everywhere. I mean, they're critical components in different engineering worlds, power generation, aerospace, defense. They're often used in high pressure scenarios, so the possibility of buckling is pretty common, Large stresses incur on these vessels themselves, so it's generating lots of points of failure, which, as we know, we can use FEA to mitigate and try to figure out where these points will be and maybe change our design to eliminate that possibility. And those failure points come from these critical eigenvalues, which we'll see in the equations in the next slide. And here is the first example. So on the right, you can see a photo actually of a pressure vessel, and this pressure vessel experienced an internal pressure where it caused expansion and buckling and points of failure on the edges. So that's what we use FEA for. We simulate stresses on these models and find critical loads and failure points determined by FEA through these eigenvalues. So the pressure vessel wall thickness plays a huge part, which you'll see in the later slides. We have an example from the text shows relation between pressure vessel thickness, wall thickness, and the critical buckling point. So they go hand in hand and directly correlate to each other, and we find these values through stiffness equations. So with FEA, we can analyze these types of things, and then we can analyze the methods taken to analyze modal shape frequencies and buckling behavior of pressure vessels. So on this slide, we dive deeper into these principal equations. These are used to analyze vibration characteristics of the system. They focus on determining the critical buckling pressure in the end. So that's based off material thickness, design, material type. This is calculated by finding the critical buckling pressure from the eigenvalue. So you can see in the first equation of the stiffness equation, we have Ke, which is the elastic stiffness matrix, Kg being the geometric stiffness, and then the phi b is the buckling load shape. The important one we're focusing on here is lambda critical, which is the critical buckling load eigenvalue. So we can then use FEA software similar to the study. I think they used ANSYS in the study. We can find the lowest eigenvalue based on shell thickness. So to find this value, we have to use a few different matrices. These are determined by the FEA, such as the elastic stiffness matrix. It's based on the geometry and material, and the geometric stiffness matrix is determined from internal pressure. In this case, it was used 1 MPa was used for initial calculations. So these values were also shown in the study and determined through FEA. So once we establish these matrices, we can import them into something like MATLAB to interpret them and find the minimum eigenvalue and determine the point at which the critical buckling will occur for different wall thicknesses. On the right, you can see a graph curve. So this was part of the study. It shows thickness versus pressure. So obviously, intuitively, you would think higher thickness, higher pressure, and well, that's right. The thicker the pressure vessel, the more of an internal pressure it can withstand. And you'll see that later in the next slide in this table we have depicting that. Okay, so here's that table. So we can use that relationship to relate different pressures to different thicknesses. So you can see from the table the thickest pressure vessel wall has the highest critical buckling pressure, which we would say intuitively. So if you're an engineer and you're designing a pressure vessel for a specific application and you have a specific pressure that you want to be able to withstand, you would design the thickness directly to be able to withstand that pressure. Say you have 3 megapascals that you need to withstand, you would want to have at least 10 millimeter thickness so that a failure is not an option. Now, of course, you have to weigh in other factors like weight and such that might create more fine-tuning between those points, but this FEA is super useful when trying to design something for a specific failure mode in mind. So we can change these thicknesses in CAD and use the critical eigenvalues and pressure loads to determine buckling points, and then go back and change the CAD if we need to. and then we can, this all comes after the FEA and initial design, which is all part of the engineering design process. Testing in this case in simulation, ANSYS, or whatever FEA software, and then going back and redesigning, simulating, and eventually reaching a final design solution to proceed on to testing. Okay, so that pressure vessel example was the main example we wanted to look into and try to go over what they did and explain how those eigenvalues come into play. But there's lots of different examples from the real world that we didn't mention already that use eigenvalues and matrices and matrix math. So on the right, you can see a diagram that many of you have probably seen in vibrations. This is a diagram depicting a simple, very, very simple suspension system. So in a suspension, we have car springs, tire spring stiffness, tire mass, car mass, all these different things. We have moments coming into play with the suspension arms. It's really cool to see all this stuff because I was a suspension team lead on a Baja team in college, and I got to design suspensions myself and use these equations to figure out damping coefficients and such, which is part of what I wanted to talk about here. In the automotive engineering world, you use these matrices and stiffness equations and damping equations to figure out the perfect damping for your car. So like an off-road vehicle, you'd want a little bit of an underdamped system, maybe if you want more rebound on your car to account for terrain maybe on a race car like an F1 car, you would want a little bit stiffer springs, stiffer compression, so that when you're going around turns, it can handle the lateral weight transfer. So all this stuff is really cool to see how eigenvalues relate to real world examples, because I can tell you when I was in college, I probably didn't focus too much on this part of it. And I was just trying to design something that worked and passed the FEA. So it's pretty cool. Natural frequencies are a big part of these equations, and they're fine-tuned to the perfect ride comfort. We also see the use of these eigenvalue equations and vectors in civil engineering for tall buildings. Sway frequencies are taken into account. In rotary machines, we have turbines, pumps, compressors. All these things have rotating components. And vibration sensors are used to compare with known good values to fine-tune those systems. So they all require the use of eigenvalues to design a perfect system. So it's not just the examples that we found. There's tons of examples, too many to go over in a 15-minute presentation. But anyways, let's move on and move on to our conclusion slide. So I wanted to bring up a few key points. I mean, the studies that we chose clearly demonstrated effectiveness of eigenvalue analysis. It's a really important tool for evaluating integrity, especially in those cylindrical pressure vessels. We can leverage FEA techniques, and we can then predict buckling and vibration behavior for complex designs like that pressure vessel or different types of FG panels. The point of FEA is to find critical thresholds. On the left, you can see an example of some sort of sheath exposed to different types of loads and their critical failure points. So we can find these deformations, patterns, and prevent failures before the part goes out into the field. So this is really important in defense industries and such that I'm sure a few of us work in. We can't have parts as engineers going out and failing. So FEA is one more step that helps us prevent this. And it's all with the help of eigenvalues. FEA provides an accurate simulation-based insight. It's cool to see mathematical methods and theory shown directly translated to this and being tools for safer and more efficient engineering. So that's pretty much what we came up with. It was really interesting to research this kind of stuff, especially with our background in some of these things. Hope you guys enjoyed it and hopefully learned something. Leave a leave a message below and we can look into them. Thank you. Bye.